Question 8. Group 7 plus just generic redox stuff. That's the context for this. Just to point some stuff out, it's very, very easy to overlook the Group 7 topic, or to only focus on things like the halide precipitate formation and the concentrated sulfuric acid reactions, and then forget about the sort of standalone bit of chemistry about chlorine, and it's very easy to forget about the sort of just halogen properties. So don't underestimate it, basically. It can be quite tricky, okay? And there's quite a lot of knowledge required, so you have to spend a bit of time doing your kind of memorization, flashcards, that kind of thing. So on with the question. A student oxidised a solution of hydrochloric acid with a few drops of sodium chlorate 1 solution. The reaction mixture effervesced, so a gas was produced, and it turned pale green. The gas formed bleached universal indicator paper. So there's a lot of stuff going on here, right? The main thing is that from that paragraph of the question stem, you're supposed to understand that molecular chlorine has been formed. First things first, let's see about the first clue, the effervescence, right? Hydrochloric acid, sodium chlorate 1, okay? You've got substances here which are liable to produce elemental chlorine if they undergo redox, because they don't contain chlorine molecules as it is. Hydrochloric acid has got chloride ions, sodium chlorate 1 contains chlorate 1 ions, but chlorine is sometimes the product of the redox reactions of chloride containing or chlorate containing things. And again, this is something you just kind of need to know, okay? They mention that the reaction mixture turned pale green. Mixed feelings about this. I don't know, I guess that might be something else, but chlorine, when it's dissolved in water, tends not to change the colour very much, but it doesn't matter too much. You are supposed to know that chlorine's a green gas, I guess, although that colour is often very pale too. Alright? The gas formed, maybe that's what they're referring to be fair, rather than the solution. The gas formed bleached universal indicator paper. Again, that's another thing you're supposed to know about chlorine. So all of these words up here are basically leading you towards one thing, which is chlorine has been made. So the first question asks for a half equation for the oxidation of chloride ions. It doesn't say to what, but the only possible answer, right, is that they're being formed into chlorine molecules. So this is a GCSE standard half equation, although writing it yourself is more of an A-level task. The first job is, if we're going to turn chloride ions into chlorine, we need to balance. We need 2 of them, and they're going to lose 1 electron each, so we need 2 electrons on the right hand side. Okay, that is as easy as half equations get, although arriving at it isn't that straightforward in this question because you have to deduce what the product is. Next question's a bit nicer in one sense, because it at least tells you this time that chlorine is the product. So that's one of the first things we could do, is just bang chlorine there, okay? It also tells you that we're working in acidic conditions. This is just basically a signpost to the fact that this is a more complex half equation that's going to require the presence of H+. So if you're being taught redox, one of the things you should be taught is that at A level, pretty much all redox reactions that we look at take place in aqueous acidic solution. So there's always going to be water present, and there's always going to be hydrogen ions present. There are lots of redox reactions that happen under alkaline conditions, but you never look at them at A level, okay? So whenever it's a more complicated half equation, it's going to need H+ to be present. The next thing is chlorate 1. You've not been provided with a formula for this, okay? Again, you're sort of supposed to know this, but even if you don't, there's a way to deduce it, right? And it requires you to have an understanding of the language of chemistry. So I'm just going to do that over here, and then I'm going to delete it afterwards. Chlorate 1 has to contain chlorine, right? That's kind of hopefully really obvious. This suffix, ATE, actually means something. Again, it's signposting that there must be oxygen present, okay? And there must be a negative charge. So all we're going to do for now is put 1O, because we don't know how many there are for now. We're going to put a minus because we don't know how much of a negative charge there is. But there must be an oxygen, there must be a negative charge. Think sulfate, nitrate, carbonate, phosphate. All of these things follow this pattern of naming for their ions. So the next thing that you're told is an oxidation state, which is 1, Roman numeral 1. That refers to the thing that's got the variable oxidation state, which is the chlorine, not the oxygen. So that means chlorine must have an oxidation state of +1. Oxygen's most typical oxidation state, apart from some certain extreme circumstances, is -2. So that means we can then check, okay, if our chlorine is +1 and our oxygen is -2, do we need more than one oxygen to make it negative? No, because at the moment we've got a charge of -1. So actually there's nothing else to be done here. The formula for a chlorate 1 ion is just ClO-. Because this isn't a brilliant example, I'm going to take this a little bit further. Okay, so that was the correct formula. We'll go back to that in a minute to do the half equation. I'm just doing this because it's an important sort of teaching opportunity, right? There's another form of chlorate called chlorate 5. That contains chlorine, it contains oxygen, it has a negative charge. But this time the chlorine has an oxidation state of +5. That's what the Roman numeral tells us. So this time you can't just have one oxygen, because that would have an overall charge of +3, which doesn't make any sense because it must be negative. You can't just have 2 oxygens, because that would have an overall charge of +1, which would not make sense because it's got to be negative. Which means that the minimum number of oxygens you need to have is 3, which means that the formula is ClO3, and then we have to check. We've got +5 and -6, so the net charge is going to be just still -1. We don't have to change that. So that's where these ion formulae are from and constructed from, and how they relate to the names. This isn't a big part of A-level chemistry, but if you can get your head around it in at least a basic fashion, it makes these kinds of questions a lot easier, because you can double check that you've got the right formula for any kind of weird and wonderful ion with an oxidation state. Right then, back to the actual question. We decided that that was the formula for chlorate 1. So ordinarily what we do here is we'd say, okay, we're going to add some water to balance out the oxygen atoms, and that's a fine way to start, but it misses something. And the thing it misses is you also need to check, first of all, whether the thing that's undergoing reduction or oxidation, in this case reduction, whether the thing that's undergoing redox needs to be balanced as well. And in this case it does. There are 2 chlorine atoms in a chlorine molecule. There's only 1 chlorine in a single chlorate ion, so there must be 2 lots of that. The reason that's important is we're going to stick water on the right hand side to balance the oxygen, because that's what you do when you're balancing these half equations. But we'll need 2 moles of water because we need 2 moles of oxygen atoms. That then has a knock-on effect, because now we're going to say, okay, well, we need some hydrogen ions over here, and if we hadn't done this bit right, we would have only put 2, when in reality we need 4. That then has another knock-on effect, which is that the number of electrons would have been incorrect. So at the moment, there's no charge on the right hand side, 0, 0, they're both neutral compounds. We've got 2 minus and 4 plus at the moment, which means we need 2 electrons, because we need another 2 minus, and the charges are balanced. Just another reminder about something I always teach is charges do not need to add up to 0 on both sides, they just have to be the same. Coincidentally, they often do end up being 0, like in this case, but they don't have to be. So, just bin that bit, make it a bit tidier. Write an overall equation for the redox reaction of chlorate 1 ions with hydrochloric acid. So again, this is a bit of a trick that they sometimes do. So they're saying hydrochloric acid, right? And people start thinking, well, I don't know how to do that because I've not done anything about hydrochloric acid yet. Well, you have, actually. Down here, or up here, sorry, the chloride ions that we're writing the half equation for, they're coming from HCl. It's just that in this half equation you don't show the hydrogen ions. But if you go back to the very beginning, these are complete compounds. So these chloride ions come from HCl, just like in this example here. The chlorate 1 ions come from sodium chlorate 1. We're just not showing the positive ions a lot of the time because they're not necessarily very useful. They don't really do anything. They're sort of spectator ions that don't undergo redox. So then, in this case, right, there's a couple of ways you can do this, but really all it's actually asking you to do is to combine the previous 2 half equations, right? That's pretty much all it's asking you to do. And so to do that, you need to check, do I have a common number of electrons? I do. If you don't have a common number of electrons, then you have to do a multiplication of one of the half equations, but in this case that's not how it works, okay? So, right, we basically just have to put everything on one line and cancel out the electrons, okay? So, I'm going to start with the reactant from the first half equation, which is chloride. Then I'm going to add the reactants from the next half equation. Including the electrons for now. I've got a reaction arrow. Then chlorine. These are both on the same side, so we're going to add them together. There's actually 2 moles of chlorine that are made. 2 moles of water, 2 electrons. Now, things that we can do. First of all, bish, bash, no bosh unfortunately, right? You can get rid of 2 electrons from either side because they're the same. So, in my case, what I'm going to do is, now that you've seen that, I'm just going to get rid of that entirely, because they shouldn't really be there, right? It was just to show the process. Then, other stuff that you can do, right? If you look at the entire equation now, you need to check if it's being shown currently in its simplest form, and it's not, right? We can alter all the coefficients. We can essentially divide everything by 2. So, I'm going to get rid of that, I'm going to get rid of that, I'm going to get rid of that, I'll deal with it in a minute. I'm going to get rid of that, I'm going to get rid of that, and then I'm just going to go back and make sure that there's 2 lots of that, okay? Because that's the simplest form of the overall equation. We've divided everything down to its simplest whole number ratio in terms of coefficients. And then finally, one last thing, it doesn't really matter if you do it this way or not, but it is entirely sort of feasible to just rewrite the first portion of the half equation so that you have HCl shown as a complete compound plus a chlorate ion plus 1 hydrogen ion, and then the products would be the same. This is pure convention, doing it this way versus another way. All that's been done here is one of the hydrogen ions that's shown there has been paired with the chloride ion to show it as HCl. I haven't looked at the mark scheme, but either of these will be acceptable. I'd be very, very surprised if it was one over the other. Okay? Right then. Again, something that's very, very easily overlooked is observations on simple redox reactions of halogens. Okay? So it says sodium chlorate 1, right, which is an oxidizing agent. That's its role up here, it's an electron acceptor, is added to potassium iodide, which to begin with is colourless. Okay? Suggest what is observed, explain the reaction that leads to this observation. So, Ki, potassium iodide, contains I-, and the iodide ion is a pretty rubbish oxidizing agent. If you remember, you learn a trend about the oxidizing power or oxidizing ability of the halogens. Fluorine's the top dog, and then iodine is the worst. So an iodide ion, right, is quite easily oxidized by other things. It's not very sort of stable as it is, right? So what that means is the iodide ion in potassium iodide, not going to write an equation, but it can be converted quite easily into iodine. Now, this is something, like I keep saying, that gets totally undervalued and totally overlooked, right? Which is the physical properties of iodine, okay? So, iodine at room temperature is a black solid. Alright? You sometimes get away with calling it grey, but you never get away with calling it purple, because the vapours of iodine are purple, but nothing about this reaction suggests that the temperature has been elevated, so you're not going to get away with that. And the solid is not purple, it's black. Okay? You could get away with, for the same mark, a brown solution, because iodine, when it's dissolved in water, right, and there is water around because we started with a solution of Ki, is brown when it's in solution. Either of those will get you the same mark. So that's your observation mark. explain the reaction that leads to this observation, right? So this is something we've mentioned already. Oh, sorry. Let's go back in. There we go. Chlorate 1 ions are a stronger oxidizing agent. That must be what it is. This is a sort of slight twist on the typical question, because the typical question would ask you about a combination of chlorine, molecular chlorine, being bubbled through potassium iodide or something, and it'd be the same outcome, rather than it being sodium chlorate 1. Alright? So the only other thing I might add is just in words, because I'm conscious of the fact it's 3 marks. Is a comment about the fact that the iodide ions are oxidized to iodine. Kind of mentioned that up at the top here, but it's probably better to explicitly state it. Okay? Right.